Size, it's good to go through it, but in actual use of it in the future, you know that these things are, well, just repeat it in the comments. Okay. Okay, the C part is the adding aspiration to override the taboo and nature influence by R square. And then this kind of a result can be very mixed. Okay? And this is just put in there for you to say, okay, there are other ways you can do in terms of aspiration. If R square improve a lot, you probably want to keep that thing in there. Okay, to override on your previous taboo list. But the R square probably not the best way to use anyway. Any questions on 3.2? Okay, 3.3, simulate annealing to minimize the AIC. This effect of different cooling schedule, of course, have a tremendous impact on this. In the initial temperature, I already said initial temperature is very difficult thing to choose. For different problem, initial temperature, some may be 1,000, some may be just 1 or 2. So you really don't know. So for this initial temperature, really become very, very much problem dependent. You just have to test it out, okay? And the cooling schedule is the same. So I myself is the following. These say like a similar annealing and a genetic algorithm, all this is complicated thing. And for this, only you do this sort of thing, especially like a similar annealing originally was developed for essentially particle physics, actually. If it's a huge amount of particles and so forth, it's almost impossible to do any computation. So that you develop something, and especially for that, you don't know what's the normalizing constant for that so-called distribution, so-called Gibbs distribution or something like that. And then nevertheless, you want to have a way to explore the space, and then that's the way you do it. In this sort of simple problem, you may say, like, it's a predictor selection, only 27 predictors. In this sort of thing, to use the simulated annealing, of course, this is an exercise for you to know how this thing works, but in practice, you would not use this, okay? Because by its nature, it's just too complicated. Because the initial temperature, the cooling, the schedule of the stage, the iteration, all these have some input in terms of the results. And I said it's comparing the effect of a proposed distribution that is discrete uniform of 2 neighborhoods or 3 neighborhoods. Now obviously the 2 neighborhoods, 3 neighborhoods will take longer because you have to search the sample space much longer. And the result may be better or may not be better. Depends. Okay. It depends on the schedule, depends on the problem, and so forth. Okay? I think by now you should realize this optimization is by no means a deterministic process. You should all know that by now. But this is precisely the point I want to drill into. Many times you say, well, computer is deterministic machine. I say, no, computer is not deterministic. In some sense it is, but for the user, because of round-off and so forth, you don't know what's going on, sometimes it becomes random. Two people doing the same thing, you can get different results. Depends on how it's computed. Sometimes it depends on the day, which day you compute it, what time you compute it. You know why? Yes, that's right. Sometimes they use the clock to generate something. Different time you generate different things, and then you get a different result. Okay? So, many times random seed they take from the clock. Actually. So, but this is precisely the thing I want to drill into you. Don't blindly just say, okay, I put this in the computer, whatever the output must be right. Whatever the output, I would say many times is wrong. You have to be very careful with that. Okay. The last one is a genetic algorithm. Okay, this one, of course, you still have these things, so-called tuning factor. every optimization algorithm has tuning factors. You know, even the say like Gauss-Newton ones, you have tuning factors. Okay. You know, step size, directions, and so forth. How you want to do it, all these tuning factors. When do you want to start, and so forth. All these tuning factors. And the genetic algorithm is no exception. You have tuning factors. For example, what's the initial population size? What's the mutation rate? You know, how should you do the mutation, and so forth. You know, each generation, how many members should be replaced? All those are tuning factors. And if change any of those, will change your result, will change your speed of convergence. But you may say this seems to be a problem, but also give you the flexibility. You know, it all depends on which way you're looking at. Okay, that means you have more parameters, you can tune it, and then you can adapt it to different problems. So different mutation rate, generally speaking, the book already says about 1%, the mutation rate, and that seems to work for many problems, but by no means universal. Depends on the problem. Some may be want the mutation faster, some may be slower. We already say if too slow, that means it was slow convergence. And too fast, that means you lost the ability to build up your strength. Okay, whatever the genetic advantage you accumulate, if you mutate too fast, will destroy them intuitively. Okay, so obviously you don't want to mutate too fast. Now the generation size. Now typically the generation size, well, the book gives you some guideline, usually about somewhere to 20 to 50 or something like that. And but again, you know, generally speaking, what you want is that this population should be reasonably large to have the genetic diversity, so to speak, so that you can explore all these. You know, combinatorial type the book called the combinatorial algorithm, and in some other literature called the stochastic, because these are what always have some random search. Remember this? All this random, right? In and out, that's random. Okay, the population size, how do you do the mutation? That's random. So sometimes it's called the stochastic algorithm. It depends on which literature you read. So all these so-called combinatorial stochastic optimization have the virtue in trying to search for the global minimum or global maximum. It's global. Whereas the like Gauss-Newton, all those kind of things are local, because you only do the local search. When you started, you do the local search. Whereas these, you know, similar annealing, genetic algorithm, all these is try to explore the entire sample space and try to get you to the global optimum. So there's a fundamental difference in it. And when you want to do the global search, certainly you're more complicated. You have a lot of local minimum and so forth, and then you want to be able to explore everything. Certainly it's much more time-consuming and complicated. You know, you want to gain the global one, well, you have to pay some price for it. Okay? C says these one parent, the fit, and the other random, or there are different ways you can choose the parents, and then how do they produce the offspring, the next generation. So there's the C part. There's three ways to do it. One is one parent is by their fitness, proportional to their fitness. The other just completely random, or both parents proportional to their fitness, and or you do the tournament type. Tournament type again, again that's try to explore broader space. Okay, because you partition. In here, it asks you say P divided by 5 groups or P divided by 3 groups. P divided by 5, of course, in this case is what? P is what? 27, is that right?
I thought it would, P is the population, right? So it would be 20 by default.
Yeah, population size you divide. So that means you divide it into 4 groups. And each group you produce one. And then you get the offspring. And this guarantee that, since you randomly partition this group, So, for one group, maybe all bad, so-called bad, but they got a chance. Otherwise, they don't ever get a chance. And this is also the reason we tell you not just use the so-called proportion to fitness, but by ranking. The ranking you tend to shrink them, the difference. The probability one gets chosen will be not as extreme as purely by fitness. Because if one fitness score is very high, then this one has a very high probability of being chosen, and then the whole population will be biased. So the tournament does have this more democratized process. Okay, and the D says a steady state. Steady state, that means what? You only change the worst one at each iteration. Or the more extreme is that to change the entire population to something new. That's the other extreme. Typically, it's the following. Initially, you probably want to change more, and when you get to the very end, indeed, so-called the steady state, indeed, you want to do it slowly, do a more local search. That's general strategy. Okay. So you can compare this with the non-overlapping generation. One extreme is to change the whole population, the other extreme only change one at a time, or somewhere in the middle is that you change half or a third of the population, or something like that. And the E says that this is called the uniform crossover. Uniform crossover means that, so here's the one parent, and then here's another parent. Let's use this. Now the offspring in here is that this one should be from parent 1 or parent 2 is randomized in here. So at each locus, it's randomized. It's sort of like almost like a random shuffle. Okay, shuffle these two. Okay, and this, of course, is not just like a crossover. Crossover is you keep a section, right, and then the other part got changed. This means what? This is almost like what? Every
locus.
Every locus has a mutation, so to speak. All right. So this is just for you to compare these. Okay. Time is up, and do you have any questions?
For the resubmission, would you like us to reprint a new one and attach this to it?
No, you don't have to. Yeah, just send me the code. We see not part of the future.
So are there algorithms that optimize the tuning parameters to optimize the optimized algorithms? No.
The reason is that every problem tuning factor is problem dependent. So there's no universal ones you can do. And then to really try to get the so-called good optimization, you really have to spend the time to explore it. The problem we look at it, even in the previous ones, it's just one variable with that Cauchy one, remember? The objective function looks sufficiently complicated. You can already see where you start and so forth, so on, can get you to very, very different places. Okay? And then you may indeed use Cauchy instead of use Cauchy once, use another, say like a genetic algorithm, similar annealing, to see, because you have several of these local maximum to see when you get the global maximum. But you can see that even for one single variable, it's sufficiently complicated. And then when you have a multivariate, which we actually have not done a lot, which I have done it before, is that you have to do it very, very carefully. Usually you have to spend the time. The best is that certain region and then you want to use your domain knowledge as much as you can, and plot as much as you can. If a higher dimension, it's hard for you to plot, but you have to slice it, at least to get some idea what these look like. Some of these things, especially in time series analysis, because it involves a lot of cosine sines, and then many times your function have lots of it. Your function indeed have lots of these local maximum, and your function indeed a lot like this. Periodic one is a case in point. So you want to find many times in this sort of problem is that you have to get to the solution in the order of 1 over n, and then localize. Then you can get. If anything else, you cannot. There are many this kind of problem, in a lot of applications. So for those, you really have to be very, very careful. Now, suffice to say, we have more or less, you may say, covered in, that the unit on so-called optimization, deterministic one and stochastic. If I classify it that way, the book called combinatorial, but many others are stochastic. And whereas like Newton, Gauss, those kind of things.